Okay, guys, can you look up, please? Look up. Can you look up? So, guys, look up. Now, what I want to do now, so like I said, the plan is a bit more practice of optimization in class, and tomorrow I'll run through the questions from the worksheet. It's important that you try them, or otherwise there's no learning value in them. So to help you with that, I'm going to do another optimization one, and I want to make it a little bit interesting, so I want to have a biology angle on it. Guys, you're not all looking up. I'm not that bad to look at, am I? I mean, I realise my hair isn't as great as yours, but I would appreciate yeah, I mean, at least I don't have to wear a cap to cover it up, you know? So, I wanted to make it interesting by making it related to a biology example. Anna, please, look up. I want to make it interesting by making it related to biology example. So the idea here was something that you did recently with column. On the x-axis is the temperature. On the y-axis is the time taken for the pink coloration to disappear. So temperature here in Celsius. So this is 0 Celsius, or roughly 0 Celsius, roughly 60 minutes. Although maybe it's more than that. It shoots up then, yeah. So maybe I'll make it like 1 Celsius, whatever. Well, no, 0 is a nicer number. Okay, so at 10 Celsius, it takes 30 minutes for the colour to disappear, and at 20 Celsius, it takes 10 minutes for the colour to disappear. And this is all the information that you have. Now, I know in this example you did more data points, but realistically, you might find yourself in a situation where you have only partial data. And you can look at this and you can see that clearly that it's decreasing and it'll reach some kind of minimum. But the problem is you haven't done enough collection of data to figure out what that minimum is. Because you imagine that if you could continue the graph, it would perhaps continue down for a little bit more, and then, who knows, maybe it'll probably go back up. So we'll use a little bit of maths and a little bit of calculus to try and figure out what this point is. So our first job is we have to figure out a formula for this shape. Now, if you have only 3 points, the best shape you can assume it is quadratic. If you had 2 points, what would be the best shape you could assume? Is linear. Now you might say, why am I doing that? Well, let's consider the extreme opposite. If I had 2 points, which is more likely to be the case? That the curve connecting the 2 points is a straight line, or the curve connecting the 2 points goes like this? So you see that the reason we say a straight line is because it's most economical explanation of what is connecting the 2 points. So by the same logic, if you have 3 points, the most economical explanation is that there's some kind of quadratic that connects the 3. Especially if it's curving like a quadratic already. So we are trying to seek a quadratic here. So we know what we're looking for is this. But we don't know the A, B, and C. We can find the A, B, and C by subbing in these points. So if I was to sub in the first point, I would get 60 equals 0 plus 0 plus C. This is great. We already have the C. The C must be 60. So now we have y equals ax squared plus bx plus 60. Okay, let's sub in the second point. So now we get 30 equals 100a plus 10b plus 60. I can divide by 10, and I can say 10a plus b equals 3. Now, I don't know the a and the b, but you could probably have a good guess at what's going to happen. I sub in the next point, and what do you think I'll be left with? What situation? I'll have simultaneous, or 2 equations. So I'll get 10 equals 400a plus 20b plus 60. Again, I divide by 10. 1 equals 40a plus 2b plus 6. 40a plus 2b equals minus 5. Now, if I want to solve these two, what would be the easiest thing to do? I suppose I could multiply this by 2 to make a 2b. So I'll have 40a plus 2b equals minus 5. And I'll have 20a plus 2b equals 6. And then I'll minus. So that's 20a equals minus 11. So I get a equals minus 11 over 20. And what's the easiest thing to give me the b? Oh, this one back here. Yeah. Sub it in. So let's see what we get for b. You have it already? Let me just write it down. 10 times minus 11 over 20 plus b equals 3. So b equals 3 plus 100. Oh, that cancels down, doesn't it? So plus 11 over 2. So that's 17 over 2? Yeah? Yeah. Okay, so now we have our answer. Y equals A. Huh? I was expecting A to be positive. Is that minus 5?
Yeah. Yes, right. Minus 5, minus 6.
Ah, so I drew this terribly. I drew my 3 points like... No, how could it be a hill shape and pass through those 3 points?
Oh yeah, because it's at the vertex is the optimum. Is the optimum activity.
This is temperature and height.
Oh.
Yeah. Have I done something stupid with my signs here? I was not expecting a negative A.
It makes sense if it's temperature and activity.
Maybe I should change that to temperature and activity then. Oh well. I think your graph is the problem.
I wanted to say it was probably Angela's fault.
Yeah. I'd say that's a safe bet.
Yeah.
Anyways, no matter, we'll continue with our calculations, pretending everything is okay. So A is minus 11 over 20 x squared. B is, what did we say B was? 17 over 2x. And C is 60. Yeah. Okay. And I don't know why it's negative, but anyways, we'll continue. We want to find the turning point. So how do I get the turning point here? Derivative, yeah. So the derivative is, bring the 2 down. So that would be minus 11 over 10. The 2 and the 20 cancel. Plus 17 over 2. And what should this equal? 0. So you get x will equal minus 17 over 2 divided by minus 11 over 10. Can someone just hit that in and give that for me? Yeah, what's that as a decimal, please? As a decimal.
Stephen, the 10a plus b equals 3. Shouldn't it be minus 3?
Or maybe. Which is it?
10a plus b
Equals 3.
It's minus 6 plus 3.
Ah, thank you. Wait, stop! Gafar found the mistake. Thank you. Guys, look up. You spotted this should have been a minus 3 because it's 3 minus 6. So that should have been minus 3. So let's just fix that. That's minus 3. Now I multiplied by 2, so that should be minus 6. Minus 5 minus minus 6. Try again, Mubarak. Minus 5 minus minus 6. 1. Okay, 1. So my A is instead 1 over 20. And what's my B then? If I sub that in here, my B will be minus 3. And then I'm subbing it in. 10 over 20 is a half, isn't it?
Yeah.
And bring it to the right is minus a half?
3 over 2.
Yeah, so the B instead is minus 3 over 2. That's minus 7 over 2. Wonderful. Okay, so I can fix this up now. That's much better. Okay, Angela, I take it back. Your graph was wonderful. Alright, so that is instead A, which is 1 over 20, and B, which is minus 7 over 2. So the derivative now, what will that be? 1 over 10, isn't it?
Yeah.
And then this one here,
Minus
minus
7.
7 over 2. Thank you. So my x instead will be 7 over 2 over 1 over 10. 7 over 2 over 1 over 10. What's that? 35. Okay, so what we're saying is if we go back to the graph, the minimum happens here at 35. Now I very roughly took 3 points off your graph. Where was the minimum on yours?
Yeah,
Was it 35?
it's around that. We were not given enough information to focus.
Yeah, but on the actual graph you drew, kind of around about 40, 35, 40. Yeah. So the point I wanted to make with this one is you can actually find the minimum with only 3 points in the front of the minimum, because you can kind of get a quadratic and project it down and find the lowest point on it. Okay. So if you can write that one down as another example, then if you can't read anything here, just tell me. I'll clean it up as you're writing it down, so it's not so messy. That's a 1.
Don't you have a bigger eraser?
Yeah, I know. This is a bit painful to watch, isn't it? Very unsatisfying. 1 over 20.
So to find the vertex, then you just sub it into the quadratic
Yeah,
that we found.
yeah. Will I zoom out? Will you still be able to read it if I zoom out?
Y is minus 5 over 4.
You got the y?
Yeah, minus 5 over 4. Hopefully.
Oh, it couldn't be. It needs to be positive.
And maybe, yeah.
I know. Let's not complicate our lives. My question was find the optimum temperature.
That's what I keep getting.
Maybe it doesn't have enough bulk.
You might need to get an update for your graphing calculator. There might be a patch for that bug that you're having right now.
You have a Cassie?
Did you write this down? What?
Not wrong.
Alright.
Minus 5.
Okay. Okay, can I continue? Do you have this? Yeah? Scrolling down? Okay. Can you tell me, in chemistry you've done reaction rates? Have you or have you not?
No.
No. You've done reactants and products? Yeah. So, have you done graphs of them? No. No. Well, you know that there's a relationship between concentration and the
Unrated reaction.
like what relationships have you done, or
No, we don't do
Concentration is equal
the
to
more-
moles over volume.
that's the only one?
Yeah.
Are you talking about like the more concentration,
Yeah.
the more the rate of reaction?
Yeah.
Yeah, I mean that's a common.
But have you done that? No, if so, then I won't do that then. Yeah.
Kind of like common concept.
No, the reason is I want to show you another usefulness of, guys, listen. I want to show you another usefulness of derivatives. So if I just go back to this one as an example, in these graphs, it's sometimes important to know how quickly something is changing. Like for example, I mean, if you have something like here, this is x and this is y, you might want to know how quickly the y changes with the x. So for example, if I draw another graph here, consider these two situations. You have a graph which is increasing like this, or you have a graph which is increasing like this. So imagine you're here on the graph, or versus you're here on this graph. In which situation would you see the greatest change immediately after the x? In the first one. Because here, if you were to increase slightly, you would see a bigger change than in this graph here. And I want you to realize that that change is actually what the derivative is, the slope of the tangent. So you get this thing in biology and chemistry a lot where you look at rates of change, which you all understand is just the derivative. So for a physics example, if this is time and this is distance, and you're looking at this here, you're looking at the change in distance per time, which is the velocity, which is the speed. But you can also think of that as the derivative of this graph here. You have the same thing going on. Like here, if I was to calculate the derivative, that's the slope. Ahmed, come on, listen, I need you to listen. If I was to calculate the derivative here, that's the slope. In this case here, the slope is negative. What happens if the slope was positive? It's increasing. So knowing the rate of change is very useful. So here the rate of change would be the derivative of time with respect to temperature. But a lot of books would write it like this: the change in time over the change in temperature. In this graph here, it's negative to the left, and in this on the right, it's positive. So I just want you to show that you do see this language a lot, and it's something we'll come back to in semester 2. But I'm right in thinking you haven't done anything like this in chemistry or biology? No? In high school, yeah, but not here then, yeah. Okay. Right, I want you to spend just the next 15 minutes practicing some more optimization, okay? And then you'll have your Skype call then. I really would like you to try and get them all attempted before tomorrow, okay? Yeah. Just one sec, I'll close this.